All right, so now we get to get into some fun stuff here, and this is talking about compounds and their bonds. Specifically, we're going to focus on ionic compounds, okay? Ionic compounds take place between metals and nonmetals. So we can identify an ionic compound pretty easily because one of the elements will live on this side of the periodic table. Actually, aluminum is included as well. Will live on this side of the periodic table, and the other one will live on this side of the periodic table. Okay, so anytime you see a compound where one element's on one side and the other element's on the other side, that is an ionic compound. Okay, we talked a little bit last chapter about how metals lose electrons really easily and thus become cations. So a good example would be sodium loses an electron and goes to the sodium ion. These cations, when you lose an electron, you have a positive charge, right? Nonmetals, on the other hand, like to form negatively charged ions. They like to form anions. Right, so they gain electrons really easily. So an example would be like going from fluorine to the fluoride ion. Fluorine's gaining an electron. Okay, so and then notice just these two examples that I gave here. We have sodium. If I found that on the periodic table, that'd be over here. We have fluorine, that on the periodic table, that's over here. So again, that's how we can indicate that these form an ionic compound. And an ionic compound is a bond that forms between ions, right? We know that a negatively charged ion will be attracted to a positively charged ion. So in this case, I have my positively charged sodium will form a bond with the negatively charged fluoride ion. This is what we call an ionic bond, right? So ionic bond is, in physics, you would call it like a Coulombic interaction, an interaction between charges. All right, and so again, so this uses chlorine instead of fluorine. They're in the same position on the periodic table. But yeah, so we have our negatively charged chloride ion and our positively charged sodium ion. They're attracted together, so they would form this compound here, sodium chloride, and we'll get into how we name them and all that good stuff later. All right, and then importantly, the ratio of sodium ions to chloride ions in this compound would simply be 1:1, because the whole idea is to balance these charges. I have one positively charged sodium ion and one negatively charged chloride ion. Together, they will form a neutral compound, a neutral ionic compound. We could get a little bit more complicated. So for example, if I had, let's actually do this. Okay, we can get a little bit more complicated. If they're not 1:1 like that, things might seem a little bit more complicated, but it's not too bad. So let's take as an example a compound that would form between lithium, a lithium ion, and what's called a sulfide ion. And I guess just to remind everybody, right, we know based on where these live on the periodic table, the charge that they should form. Right, these first columns, they like to form +1 ions. The second column, +2. We skip the transition metals. We'll talk about this in a second, but these are more complicated. All right, but we jump over there, and this column we know likes to form +3 ions. We can do the same thing from the other side, but we got to skip over these Nobel gases because they don't like to form ions. Remember, the reason why elements form ions is in order to complete their octet. Well, the transition metals are already full, so they're pretty good, they're happy already. Fluorine, or the halogens rather, fluorine, chlorine, bromine, iodine, they will gain an electron to form -1 charged ions. Oxygen, sulfur, selenium, they will gain 2 electrons. And then nitrogen and phosphorus, they'll gain 3 electrons to form anions that have a -3 charge. So this was an example between lithium and sulfur. We know lithium should have a +1 charge and sulfur should have a -2 charge. So just to remind everybody, we learned last chapter how we get the charges of ions just by looking at the periodic table. Okay, so now we have this example where we're going to form an ionic compound between lithium and sulfur, right? Well, I can't just have this be a 1-to-1 compound because lithium has a charge of +1, but sulfur has a charge of -2. So if these were to form in a 1-to-1 ratio, this thing would still have a net charge of -1, right? I'm just going to add up the charges, and that still takes me to -1. So instead, we have to have 2 lithiums to balance out the -2 charge on the sulfur. Okay, if I have 2 positively charged lithium ions, they'll cancel out 1 sulfide ion, which has a charge of -2. And there's an even sort of simpler way to do this that they teach you, which is you take the charge of the 1 ion and bring it down, and that becomes the superscript, or the subscript rather, of your compound. And we do the same thing on the other side, but we don't write the 1 here, right? If it's a 1, we just leave it off altogether. Okay. Likewise, if we go to barium chloride, again, we have this situation where we're going to need 2 chloride ions to balance out our 2+ charged barium ion. So if we have, we're going to write our formula, and then we got to figure out the ratios. Well, again, we can do this sort of cross thing, where since I have a +2 charge on barium, I need 2 chloride ions, and since I have a -1 charge on chlorine, I only need 1. I'm sorry, we need 2 chlorides and then 1 barium. Likewise, if we have aluminum and oxygen, again, we could figure out these charges based on the periodic table. We're going to play the same game where I know I need aluminum oxide, but what numbers go here? Well, again, I'm going to bring down this charge to replace that value, and this to this one. So this would be aluminum 2O3. Okay. The only time that this doesn't work, or you're going to rather have to do a little bit more simplification, is when you always put like kind of like a fraction, you always reduce these molecular formulas as much as possible for ionic compounds. So what do I mean by that? Well, if I had magnesium, I look on my periodic table, and we'll do magnesium and oxygen. If I look on my periodic table for magnesium, that lives in this column, so it has a +2 charge. If I look on my periodic table for oxygen, that lives in this column, so it has a -2 charge. Okay, so magnesium's +2, oxygen's -2. So magnesium oxide, I would be, if I follow this rule, I'm going to bring this one down here. Bring this one down here. So it'd be Mg2O2. Well, those aren't reduced, right? I can reduce this further to just MgO, and that would be the correct molecular formula. So if you can divide, in this case, I could divide both of those subscripts by 2 and get a smaller number, then you do that. You reduce your subscripts just like you reduce fractions. I couldn't do that over here, so that's why that remains Al2O3. Okay. All right, so now let's start from scratch here. I'm just going to give you the elements and ask what the molecular formula is going to be. So what are we going to do? We're going to go aluminum, or lithium and chlorine, and then we're going to do exactly what we've been doing before. We're going to look on the periodic table and determine the charge of these ions. So let me erase my markings here. It was lithium and chlorine. So lithium lives in column 1, so that would have a +1 charge. Chlorine lives over here, so that would have a -1 charge. Oh, +1, -1. So then lithium chloride, I don't really have to, it's not too complicated to see that I would just leave it like that. I don't have to worry about what any subscripts are. They're just in that 1-to-1 ratio. So what about magnesium and fluorine? Make a little bit more room for the third example. Magnesium and fluorine. Again, I got to find them on the periodic table to find their charge. Magnesium lives over here in column 2. Fluorine is another halogen, so that will have a charge of -1. So +2 and -1. So magnesium fluoride. Again, we're going to do the cross. That 2 comes down there. The 1 would go there, but since it's a 1, we don't really write it. So in this case, MgF2 would be the correct molecular formula for this ionic compound. And then we did magnesium oxide in the previous slide, but again, just to sort of hammer this home, magnesium has a +2 charge, oxygen has a -2 charge. So when we do our cross, we wind up with Mg2O2, but we can further reduce that to just MgO. So that would be the final answer for the molecular formula of that ionic compound. When we're talking about ionic compounds, binary ionic compounds, which just means that there's only 2 elements involved, we kind of have these 2 categories. The first is this type 1 compound, which means that the cation only has 1 possible charge. Every example we've done has been that, okay? So really what I mean by type 2 is it could have multiple charges, all right? So this is where we go back here and we fill in this like more complicated tidbit here. It turns out that these first 2 columns, get rid of my markings. In these first 2 columns, as well as aluminum, you know what the charge on the ion is going to be just by where it is on the periodic table. Magnesium's always +2. Aluminum's always +3. Sodium's always +1. There's never any sort of discrepancy. So these would be these type 1, okay? Type 2, again, it could have multiple ones. So it turns out that these transition metals, the reason that we've been glossing over them thus far is because they could have multiple charges, all right? You don't really know, you wouldn't know just by looking at the periodic table what it would be. So for example, there exists both an iron with a 2+ charge and an iron with a 3+ charge. Okay, both of those are naturally occurring iron ions. For the purposes of this class, you're not expected to know what the possibilities are. You're going to have to be told that in some way, shape, or form. Okay, so you don't have to worry about trying to memorize what these transition metals are. You just have to know that they could be multiple things. All right. So that makes it sound more complicated. So again, like this is just a good picture of all the different possibilities that we have here. And these are just like a small sample to illustrate that there are some differences. I will point out that these right here, silver, cadmium, and zinc, are considered to be type 1. There's only 1 naturally occurring ion. I don't really care if you memorize that in my class. I don't like memorization. So I like to just keep it simple and say all transition metals, everything down here, we're going to have to be told what the charge is. Okay. And we'll see that we write these a little bit differently as well. But basically, if you want to memorize those exceptions, I'll accept both answers when it comes to it. But if you don't want to have to memorize them, I'm perfectly cool with that. Okay. So, yeah. So first of all, let's just make sure that we can figure out what the molecular formula is going to be. In the next lecture, we'll talk about naming them, and we'll see that in the name, for example, we have iron with a 3+ charge and iron with a 2+ charge. We go about naming these compounds differently, but we'll get to that in the next lecture. For now, we're just focusing on being able to write the molecular formula correctly. Okay, so same process as, but actually really nothing different than before. You're going to do the exact same sort of thing, right? So if I want to do an ionic compound between iron with a 3+ charge and the chloride ion, which always has that -1 charge, I'm going to start by just writing my molecular formula and then cross. So this would be FeCl3. What about iron with a 2+ charge and oxygen? Same sort of idea. This 2 comes down here, this 2 comes down here. But what do I do in such a situation where I can reduce it further? I'm going to, just like we do with fractions, I'm going to reduce it to just FeO. And then lastly, we have lead with a +4 charge and oxygen with a -2 charge. So again, we'll do our cross. Am I done? Hopefully you can see, just like in the previous example, it can be further reduced, right? I can divide both of these by 2. That would leave me with PbO2, right? Dividing both of these by 2 to get my final answer.